and welcome. Thank you for coming to my talk. The title of my talk is Dead Programs Tell Tales, a peek at Coredumps. So it's mostly an intro into what Coredumps are, how to generate them, how to use tools to pick at them, mostly just an intro to debugging production issues or even development issues with Coredumps. I hope is useful. So just a little bit about myself. My name is Sumtochi Onyekure. I'm currently a software engineer at Fly.io, where I work on a distributed system called Corrosion that is open source and written in Rust. Throughout my career, I've worked up and down the stack. I originally started out as a front end dev, but right now I'm doing more of systems engineering and distributed systems, networking. I mean, hence, so a lot more system engineering. I mean, hence I'm at SysConf. So yeah, I really love what is being done at this conference. And just something else about myself, I like to read. So my current read is computer system, a programmer's perspective, which I think is a nice foundational book. And then Surprised by Joy, which is by C.S. Lewis. I think he's pretty popular. So outside of tech, I'm like, you guys have lives outside of tech. But I'm only joking. I do watch a lot of movies. I used to run. I'm not doing that much right now. And one movie I'm looking forward to is Fallout. I think it comes out in December. So yeah, if you're a movie freak, reach out. So yeah, let's get into the meat of the talk, right? Cordons, right? I think if you've written like some C or Rust, unsafe Rust in this case, or C++, like worked with some low-level languages, you've probably encountered this error somewhere. I think I did encounter this probably much earlier when I started to fiddle with C, but I was kind of like, you know what, I don't have time for this. Looking through my program manually, trying to figure out at what point I made a mistake. Sometimes it's like maybe you didn't allocate the memory properly, something like that. But actually, as time went on, I came to realize that this actually meant that the program has dumped some of its memory to disks, right? And I could actually go take a look at it and figure out where exactly or what is the problem with my program, right? Normally, I'll just add logs, look at things here and there, try and fix what I think is failing, and then run again, right? But with Codoms, the system essentially dumps every access memory, the whole memory address space of that the process was using while it was running to digs so that you can take a look at it. So yeah, what is cordumps? What are cordumps? A cordump is a snapshot of a running process at a particular time, right? It basically takes up like all the contents of the memory registers, the stack, the heap, any memory map files that the process might have been using. It also gathers some other metadata like the current process ID, like signals, current pending signals that the process had received, or the signal you received when exiting, right? So it just basically gathers like all the context and the memory address space that a process was using at the point that it exited. It's a very good analogy is like the black box in an airplane, that records, like, it keeps like a record of some historical data so that when the plane crashes you can actually go back and that's why I say, oh, we're looking for the black box because it contains information that can help them deduce what might have caused the plane to crash. So that's kind of the analogy. So when you have a crash like that and the system cordons, it's actually bringing out some information that can enable you later, way past the time that the process exited, to actually take a look at what the process was doing. So it's very useful for post-mortem debugging, right? It's useful for very tricky issues that seem to only reproduce maybe in production, right? You try everything on dev, the issue isn't happening. A lot of esoteric issues like seg faults, invalid references, illegal instructions, right? The CPU receives an instruction and it really doesn't know what to do with it. Memory leaks, maybe over time, your process just seems to be ballooning more and more memory, and you really can't figure out where the leak is coming from. Data races, right? You have different threads, there's synchronization issues. So just things like that that could be very hard for you to see when you're running in dev. Using a cordon can help you actually deduce where exactly these things is coming from, because I mean, you can't log all the data structures, you can't log every single thing that the process is using at that point, right? Or you might even be able to log the ones you have access to, but maybe the problem is coming from like an underlying library. In that case, it becomes much trickier. So yeah, what information can we deduce from a cordon, right? So the cordon can tell us like which function was currently executing when the program crashed. It can let us know what arguments were passed to the function, who called the function. It can give us a full backtrace, basically the whole process address space, any data that it had on the stack, on the heap, any local or global variables that the program had while it was executing. We can actually take a peek at it through Coredumps. So just a little bit about how Coredumps are generated. Most times it's actually on when a signal is received, right? So when for certain signals in on Linux or Unix systems, right? When a process receives those signals, they're supposed to terminate and produce cordons, right? Depending on if you have cordon sets, because there are a couple of settings that would, not let it produce a cordon, because they can actually be quite large. So 6F. So when a segmentation fault happens, what's actually happening is that maybe it's trying to access some read-only memory, or just a part of the memory that it doesn't have access to, or just an invalid memory address. And then the process receives like a 6F signal from the kernel, and then it will terminate and produce a cordon. But a process actually doesn't necessarily have to terminate for it to produce a cordon. There are tools like gcore, which is like a wraparound GDB, which is that can attach itself to a running program and then produce a cordon without necessarily terminating the program. So you see this very useful in production. Maybe your program is exhibiting some weird behavior and it's running in production. It's just like fading in a silent way that you want to know what's going on, but you don't want to bring down the service from your users. You can actually use some tools to get a cordon at a certain point, but it doesn't terminate the program. So yeah, just some things you might need to enable on your system if you want to actually have it produce a file is you have to set up ulimits, basically adjust the resource limits for cordons. So that's basically what ulimit is saying. I feel like on most systems it defaults to 0, which means like there's basically no size, no space allocated to cordons, and then just setting a pattern for the cordons, like where and how the cordons would be named, basically the location of them. You have to ensure that the process has enough permissions to write to that directory. And then if you send any of these signals, it doesn't actually even have to be, if you have like a process on your computer and you're just curious what it's doing, you can actually just send a 6F to it, right? You can just get its PID and send a signal, and then you would get a cordon back. So for picking at cordons, GDB is like the most popular tool for this by far. Most of these native debuggers tend to be able to process cordons and help you take a peek at them. They have like a standard format, so you can actually build your own tools. They follow the core file ELF format, which is the executable and linkable file format. So there's actually like a standard of how data is packed on these tools. I don't think all operating systems follow that standard, but for the most part, you could get your own tools. But GDB is the most popular tool for this. With GDB, you can actually list, what the register is what are the contents of the register, the process memory mappings, what virtual address space the process was using at the point where it exited. So yeah, this is what the commands look like. You basically just give it both the binary and the cordon, and it would open up, its terminal UI for you to be able to give GDB some commands and take a peek at what your cordon is doing. So just something to say is that the binary you gave, which is like the binary your program was running under, if it's missing something called debug symbols, which are additional informations about the symbols that the compiler has put in the binary, right? It's how GDB can be able to tell you what line of your function the let's say the codump is happening at. So if your production binaries get stripped of these debug symbols because they do inflate the size of the binaries a bit, or if your binary is missing production symbols, it might, like, GDB will still be able to process it, but it might be limited in the information that it can give you. So different languages have different ways of tuning the level of debug info that you can have in your compiled binary. So that's just something you might want to do, like when building your binaries. It's like, okay, how can I put in more information? There are certain system languages that GDB supports, like feel C, C++, most of the Go, Rust. So it has like some language support, but it doesn't work for all languages. But you still can see the data like that the Coredumps has in GDB. So something else you can also do is like you can strip the file of the debug symbols, but link it in later at the point where you'd like to debug the files. Just a little bit about registers. Registers are very high speed, very small memories in the CPU. If you remember the memory hierarchy, like registers at the very top, they are very high speed, so tend to be utilized a lot. So typing in info registers in GDB would dump out the content of some of the registers. I'm not sure how visible this is, but I feel like there are a couple of them, maybe up to 16 general purpose registers that each thread might have access to. So if your program is multi-threaded, it's so different threads running simultaneously. Each of them would have access to their own registers, right? So I think they're used for a bunch of things, but about three of them, are the ones you normally look out for, because what is stored in them is normally static. So like the RIP, and the name also changes based on the architecture that you are. So this architecture here is for x86. So for RIP, that's the instruction pointer, right? So it points to the address of the currently executing instruction. So the program counter would update, and then the CPU would execute the instruction at that address. And so there's the RSP. When a program is executing, it has access to a call stack, right? A definite address in memory where it has access to, that it uses. When it's calling functions, it adds data to the stack. So this points to the current top of the stack, right? And then the base pointer is like the base of the stack for the current executing function. So it's kind of like a delimiter for the different frames for different function. And then some of these ones also take like the first to six, that's the RDI and RSI, the very last line. Basically, these registers, they store the first few arguments in the function. So if your function has first few arguments, it might get stored in a register. If it has more than that, more than can fit into the available register, it will get stored on the stack. So just a little bit about the stack frame analogy. I'm sorry if this seems far removed. We would have a demo like very soon. I feel it can be very hard just following things up like this without someone actually demonstrating it. So yeah, the stack, right? Like I said, each thread has access to like a specific area of memory where it's basically adds data, very quick access. For each function that is executing, it has like that first in, first out, right? So when a function is executing, it gets pushed. Its arguments first get pushed on the stack. That's if it has more than six, because the first six might get into the registers. And then the return address, right? So this is the next instruction that will get executed after the current instruction, after the current, that's the function that is about to be called finishes. So basically, when the stack is being rewound, rewound, the return address basically holds the next executing function, right? Then the RSP, which is the stack pointer for the previous executing function, gets the previous pointer gets saved onto the stack too. And then the function, while it's executing, might also push on, local variables, basically allocate data from the stack. But when it's done, right, those areas will get deallocated, and then it would basically rewind back to the return address and start executing from the last function. So yeah, it's time for the demo. 1 second. Screen share. I'm just going to reshare my screen again, just to hope this is working. Okay, just to check. Okay, yeah. I think you guys can see my screen now. So I just have like a very small C program just to illustrate this a little bit. It's calling a bunch of function, but I think the core of it is basically happening on this line where we are trying to assign an integer to a null pointer, right? So that's obviously going to cause a seg fault. So we're just going to run the program and then just check out what we can glean from GDB. Just first I'm going to build it without any debug symbols. I feel like that's the default when you're building with GCC. Let's just see seg fault. Okay, so we have a file here, right? So it just hits a couple of logs and then it says seg fault, but it is not Coredumps. So let me just set my limits. Limited. Right, what else? sysctl. Just check that the kernel pattern is set correctly. I hope this is visible. Sorry, just increase the false. Okay, so let's check that up. Directory is actually created. Okay, let's go again. Okay, yeah, so we should have some Coredumps now. So yeah, it's basically, so with the core pattern, you can set what the name of the function is supposed to look like. This percent %p says that, the PID of the process should get appended to the file name. So yeah, let's just launch GDB here and give it the file and then the Coredump, right? Was asking to enable some debug info. So I'm going to do this again, but with debug infos enabled. But I feel like not every binary that you might have access to might have debug info enabled. So it's also useful to just see what you can find out if you do not have access. I feel like different compilers, you can tune them to different levels. So you can just play around with that to see. So let's take a look at the backtrace. So we can see, okay, main was called and then function 1 and then function 2. And then we can actually disassemble, which we can use this command, disassemble, which would disassemble the main function. And we have GDB pointing to like the command that was executing when the seg fault happens, right? Yeah, it's assembly, but most of these move commands, they are actually instructing the CPU to move some data from maybe the register to the stack or for the stack to register. And this is actually 0x2a is actually 42. If you remember our function, right, we are trying to assign 42 to the pointer. So it's actually saying that we should move 42 into the address that is stored at RAX, which is one of the general purpose registers. So we can use info registers to see what is stored at each register. So we see that the address is 0, an invalid memory address, and that's what caused the seg fault. You can also just print if with the print you get this, and to also get more info about the frame, right? So this is just giving us some information, right? The RIP, which is like the instruction pointer, is pointing to this in function 3. So symbols, just to get what GDB knows about that particular instruction. So it's just telling us like, okay, at a particular section, it doesn't have the full file, so it's missing some debug infos, but it's somewhere in function 3 that we're trying to execute, right? And then this is the return address, basically, that was saved previously from the other function, right? So we see this is function 2. So this is what's going to get executed when this function returns. It's telling us where to find locales, and let's see the stack pointer. Sorry, I should print that. So if we print the RSP, we see this is like the pointer to the top of the stack. So if you're looking at something, let's say you're looking at your disassembler, right? And you see something that is being moved onto the stack, you can try to print it out from here. So in the backtrace, right, we're going to try to find out basically what string was passed to function 2. We can switch frames here. So, okay, frame 0, we want to go to function 2, right? Some values of the registers would get like updated back to like the stack pointer now. This is now the stack pointer for function 2, and then the base pointer for function 2. So they've been updated, which you can see that it differs from what it was previously as function 1, just because of that. But the registers for the arguments haven't, right? So we can find that out from there. So one thing we can do is disassemble function 2, right? And then we see that while it is executing, it moves some data, right? Which the RDI is normally the register that has like the first argument, and the RSI has the second argument. So when you see an E instead of I, it means that it's utilizing just 32 bits out of the 64 bits of the registers. So they were moved onto the stack, right, at this point. So let's see, let's just print what. So the print command, you can give it addresses. You can also subtract. This is basically telling the stack grows downwards, right? So the earlier functions would have higher memory addresses. So it's basically saying, allocating some memory on the stack and then moving the arguments to a location on the stack, like below. So the addresses are getting smaller. So that's why we have minus signs. So the RDI has been moved to, so we can use X to print, let's say, the data 10 giant words, which is 8 bytes from this part of, right? Because we are looking for, we're trying to figure out where the first argument. So let's see if we can have GDB tell us what it is. Oh, can't access memory at 1 second. Okay. Let me just bring this to. Let's just see. Sorry. Mostly is mostly an exercise in digging through hex dumps and trying to figure out what it means to. Okay, giant words. Let's see. Okay, I think so I want the first 8 bits at this location. It says the same. Let's see. Okay, and then if we have info registers, right? The base pointer, so we know that the return address was pushed to the stack before the base pointer. So it would be at an earlier address. So we can print, also see the data x and gx from the base pointer, which is here. So this was the previous base pointer that was pushed to the stack. And then this was the previous instruction. So if we do info symbols here, oh, sorry, that's the wrong one. So yeah, we see that this is function one. So it's going to, by the time it returns to function one, it would try to execute this program. So that's, just trying to figure out what part of the stack it's currently is at, sorry, frame one. So these are the popular commands from GDB. Trying to see if I can find the string. Sorry, use assembled. So IBP. I'm trying to print the next maybe 5 addresses. The first one, we should be able to get the string from here. Okay, finally. So it's not a demo if something doesn't go wrong. I was probably missing the identifier. So yeah, by digging through the stack, we are able to determine, okay, what function was passed here. And the same thing for, the second int, right? We could also do the same. It is stored at minus 1c from the base pointer. And just to see that. So it's in the lower 4 bytes. So G is for 8 bytes. So we probably just want a word instead. So yeah, 46, 40, sorry, 4D, which is 77, which was what was passed in. But this is sort of more stressful than it should be because we didn't build it with debug symbols enabled. I just wanted us to go through the process a bit because the core file that you might have access to, or the binary your program was running under, might not have been enabled with debug symbols. So now we have debug symbols. That's what this -g kind of does. Oh, I should have made a different file. Okay, just debug. So let's try and trigger the segfault again. So yeah, if we visit root/cause, we have a second Coredump now. It's basically the same thing. I just want to show what it looks like when GDB actually has access to the debug info. So it actually tells us the exact line at which, and you can do stuff like list, which will show you some part of the source code that is around a function. The backtrace now has way more information. We kind of didn't need to dig through the stack to figure out what value was passed to function 2 because GDB is ready to do that for us because it has access to more information from the binary. Can also see how the process address space has been mapped out using info mappings, and info types tell you, this might be loading a lot, but it will tell you, like, if you're running like a program, you would see what types GDB knows about from using this. So sorry, 1 second. What else? I feel like the registers information would still be the same because, right, it's just dumping out content. So yes, from if let's say this happened, right, from just looking at what's happening, and GDB is straight up telling us what line it is that the seg fault is happening at, we can deduce what's going on in the function. Is that 5 minutes? I don't know. Was that a timer? But I'm almost done with the demo. I did have a Rust file that I wanted to sort of demo a bit, but I think I'm slightly at time. But just to show what's that like, I had like a deadlock file just to show what it might be like if you're doing something in Rust. Source file. Kind of, it's just a small program to set and get items in a map, basically. But we have a deadlock, and we get when we're going to try and get something that is not in the map, because we'll take a read lock here and then try to write here, but we're still holding on to the read lock. It's something that might not be obvious in an if-let statement, that we actually do not release the variables that are held when we enter the else statements. But if I just build that and run it, right? Deadlock app. Okay, sure. Just to show, so if we get lang, things work. But if we get lang, which is not set, we have things, it's basically hung. So if we didn't want to exit, if we didn't want, the function is basically running, right? And we don't want it to exit, we can use gcore. But first we need the PID. Income out of time. But we can use gcore to also, I think it creates a core in the current directory. So we can just quickly look at this at GDB and then I'm done. I just think not everybody writes C, and I just wanted to show, okay, I'm not in the deadlock directory. Okay. Okay. So in this case, we see that, when it's loading, it's reading symbols, right? It's a debug build, so it has symbols enabled. I don't think we'll have time to get to that, but in Rust, you can actually tune the level of debug symbols that you have here. So not very high. I think 2 is the highest, but at least something. So you can see the backtrace. So there are different threads. So thread apply. I think it's thread apply all. So basically, to see where each thread was at, it's a lot of text. I think it gets, can get complex for big programs. Like, you have to take time to. The C program was a lot simpler. Like, we just had a couple of functions there, but this one is using like Tokyo. Tokyo is pulling the function, so we have way more activities going on. Yeah, just to show you what that looks like. If we, I hope this is, we can switch thread, I think, using thread 1. So let's just go to thread 1, and in that backtrace we can see what's like our handle CMD is being called at frame 10, so we can switch frames here, use frame 10, and it's telling us at what point our program was stuck. In that way, we can list to see things around. We can do things like info locals, right? This tells us like what local variables were on the stack when this was executing, and we can actually poke around into different functions, right? And see the internals of probably a library that maybe we're suspecting the problem might be from. But yes, I think I'm going to stop here just so that there's still some time for questions. Stop sharing. Okay. For questions, yeah, GDB is the most popular tool actually. I know you can use object dumps, but that will just give you like the different sections. It's just like for seeing how the code dump is structured. But I don't know any other tool. Like there's also LLDB, which is just like a GDB alternative. But I don't know any other tools that are actually very popular as GDB. And yeah, there is a part of it. Sorry, I'm answering the question by Funanya that says, are there any other tools aside GDB, and how does one build intuition in investigating the numerous trails of information? So yeah, there's actually is more art than science. That's what I'll say, because most times when you're downloading core DOMs, it's going to be like maybe some libraries are missing. This is a it's very, even the Rust program is relatively small. A real production binary is going to be much larger. Actually, I had extra strings, but time is already fast spent. But yes, production binaries are going to be much larger. You can actually have a codon that is as large as like 20 gigs upwards, so like a lot of data, right? And that's something to also be mindful of, is that you can have sensitive data in codons. Like if your program is processing like tokens, stuff like that, right? It's going to appear in codon if someone has the time to dig through the data. So it's also sensitive data in that way. Yeah, so it's mostly causing crashes yourself. You don't actually even have to crash the program. You can actually just, like we showed with Gcore, right? Create a core file and then dig around, right? What types does GPD know? I find that it's much harder if GDB doesn't have access to debug symbols. Like you can still get stuff out, but it's way more harder because it might not know the type that an address, what type is stored on an address, right? Things like that. So yes, I don't know if I have more time or
Some, hi, Samsi.
hey.
um, sorry. So we're at time. Thank you
Okay.
so much
Thank
for
you. I
presenting.
love this.
Um,
Thank you.
yeah, thank you everyone for attending, and thank you so much, Simta. This was cool. I really liked the talk. This was really good.